So now, today, we're going to be talking about the spring and all of its facets, the force of a spring, the work done by a spring, in context of work done by a varying force here. That varying force for us will be the work that's done by the spring force. So let's introduce that. So section 7.4, work done by a varying force, or in our context, work done by a spring, because we're going to skip the first bit of that as we don't need it everywhere. So let's say that we have a spring resting on a table and mass spring system resting on a table, and the mass is at position 0. So the spring is attached here, and then let's say we displace it to the right. Well, when we displace it to the right, there is a sort of a tension in this spring that wants to, say, restore the mass back to balance, or restore the mass back to its initial position. So the equation in red is called the spring force, sometimes called the restoring force, because the spring force wants to restore the mass back to its first position, which in this case is x equals 0. It's always trying to get it back to balance. It's always trying to get it back to the state of rest, restoring force or spring force. So this equation in red is what we call the spring force of the spring that's trying to bring it back to balance, trying to restore it back to 0. Restore what? Restore the mass back in letter A. So now in B, we've displaced it. So now it wants to get back to A, but take some time for that. Spring force or the restoring force. Okay, same thing. And also commonly called Hooke's law, because Robert Hooke was the guy to first come up with this equation, this relationship. So let me just write that somewhere. Hooke's law, spring force, restoring force, whatever. Same thing. I'm gonna call it spring force. So I'm gonna do F sub S for the spring force. And it's negative because it's always gonna go opposite the mass's motion. We're gonna talk about in time what kind of energy exists at the ends, and the speed, the kinetic energy, and velocities, and how they interchange back and forth, and have nice little graphs of kinetic versus potential energy. But for right now, I just wanna get the basics. So in step 1, or letter A, if we were to look at this is a example of simple harmonic motion, which we'll take care of in chapter 15. But on the number line, or the unit circle, this mass here at x equals 0 would represent angle theta equals 0. Starting position. If you imagine the x-axis here, this is 0, this is 90, 180, 270, 360, right? Periodic. Sine, cosine functions. All of it is related, but I digress. So we start here, angle theta equals 0. This will be 90 in letter B, 180, 270, 360. We have a full period. That's to come later when we talk about simple harmonic motion in its full detail. And then we can graph this motion as a sine wave or a cosine wave. And we can also talk about the energy that exists between the sine cosine functions. There's a lot you can do with the spring. Okay, so this keep it simpler than that. The restoring force would be Fs, negative k delta x, and k represents how strong the spring is. Every spring has its own strength. its own spring constant. Um, Technically, spring constant, spring strength. The springs in your hydraulics or your tires and on your car, okay, they're going to be of a great spring strength versus some little spring that you find around in your classroom lab. So every spring has its own strength, so spring constant. And delta x is the displacement from zero. So between xi equals 0 here and x final, that's not 0. Whatever it is, doesn't matter. It's not 0. There's a displacement that's can be calculated. And the spring force is directly related to the displacement from 0. So one other thing that we're going to talk about soon is that the spring force, like the gravitational force, is a conservative force. Therefore, the distance that you pull this mass from 0 is going to be the same distance to the right as it is to the left. My pictures don't depict that, but not to scale, but that's what happens. If you ever notice that, but that is what happens because the spring force is a constant, left and right. So as it goes to the right, comes through, it moves, it's not stopped here, it's still moving with a speed of kinetic energy, which we'll talk about soon. So I pulled it right, and then it moves back to the left. It's moving with the speed v. It hasn't stopped. It's going through 0, and we'll talk about why in time. And then it comes back to x final not equal to 0, the same distance over to the left as it was to the right. Let's say if it was 3 centimeters to the right, it's going to be 3 centimeters to the left, and back and forth and back and forth. It's frictionless. So we're going to close it off to the environment. If that were so, then it would go back and forth the same distance to infinity. Never stop. Since there's friction and since there's air resistance, it's going to slowly come back to rest here. And that's our fifth position here. So if we were to follow this on the number line, this would be 90 degrees or pi over 2. Right. And this would be 180 or pi. And then this would be 73 pi over 2. And this would be 2 pi, full period, 360. And then we start again. Periodic functions occur at regular intervals. Every 2 pi, the sine and cosine functions repeat. Get this backwards, every pi, we have an asymptote on a tangent line, but well, I get those screwed up. But sines and cosines is what we're going to be dealing with down the line to help us understand waves, wave functions on the large level and on the quantum level. So the spring and its physics, dynamics, very important to understand. Any questions?
Can you explain all the angles again, like what they mean regarding to all the letters exactly?
Yes. Now, if you take a look at the XY plane here, you can track the motion of a spring or any object on a number line by its angles. So here, if we start for the unit circle goes from positive y-axis and goes all the way around in a circle, right? So this would be 0 degrees here, and if we go here to be 90, this would be 180, and then this is 270, and this is 360. Are you guys not familiar with this in your math classes? But anyway, that's what's going on in terms of angles. But in terms of let's try to think of this. But yeah, that's that's where we start. So, and this would be in terms of degrees, and then in terms of radians, this will be 0, pi over 2, pi, 3 pi over 2, and 2 pi.
Yeah, I got it.
All right. Yeah, and then but then you can map like because the reason why you do this for the spring is because it's a periodic motion. It happens regularly. It's harmonic. It's ordered. It's, this is an example of simple harmonic motion. We're going to see the difference between this being simple harmonic motion and say a wave coming in to the shore. That's not simple harmonic motion because there is no kind of restoring force. Although it is periodic and it happens regularly, it's not the type of regular nature as your spring force here, which is an example of simple harmonic motion, which we'll explain in detail in other chapters. Okay, so that's the spring force. So the spring force, we get back to the simple part. So spring force is Fs is negative K delta X. It's always going opposite the motion of this mass. And as the topic shows, we're now going to talk about the work that's done by the spring. Okay, so let me just give you the formula because I don't want to belabor you with the small calculus that I'm about to do here. You won't need to do this on a test or anything like that, but it's just a kind of a nice stopping point to see where things come from. But again, just concentrate on the formula that I'm going to write down. So as we know, work done by any force, okay, is whatever that force is, force, whatever. Let's see, let me just do this here. So work done by, right, that. So total work in any system, it could be one force, it could be many forces. It's going to be the net force multiplied by the displacement, okay? And what you call it, the work done by the spring would then be work done by spring is going to be the force of the spring times displacement. All right, and we already know that the force of the spring is going to be K delta X. Okay, so this becomes negative K delta X delta X. You might say to yourself, okay, well, this is going to be negative K delta X squared, right? Well, not quite. So we have to do something because we can't just multiply because this distance or this displacement actually varies. So we have to do an integral on this function spring force in order to get the actual work done by the spring. So again, do not worry about this step here. But let me just give you the formula. So work done by the spring will be equal to this formula, 1/2 K delta X squared. That's just giving it to you and then do it in problems and stuff. So that's going to be equal to something later when we, which is the same thing as it's the change in potential energy of the spring. Potential energy, that concept comes down the pipe. So this is our formula that we're about to derive. Calculus here. So the work done by the spring be equal to, the limits from the beginning point to the final point, final minus initial, force of the spring, delta X, but in calculus nomenclature, this delta x becomes dx. It's the same thing. Fs dx. Well, now just stipulated that the spring force is going to be a constant on either side of the spring. We cannot take the integral of a constant. So we got to bring this guy out. Or actually, let's see if the whole thing was constant. Let me erase this. Rewrite. Oops. We're going to have, so Fs is negative k delta x times delta x, but in calculus nomenclature, it's dx. The k, this is a constant. It's a spring constant, so that comes out of the integral. You cannot take the integral of a constant. So k. This becomes x dx. You know it's going to, well, I took out the delta because the delta is already taken care of by the limits here, by the boundaries, the final and initial. So it's just x that we're trying to integrate. So when we do that, this is going to just, become the antiderivative of this is just going to just be x squared divided by 2. So again, that becomes, and this is work, and that can simplify to be 1/2 k, and the limits are I to x final. That's why it's a delta, and the final result is 1/2 k delta x squared. So again, all that stuff here, don't worry about it. This is what the work done by a spring is. This is the formula for work done by a spring, 1/2 k delta x, but it's always nice to see where stuff comes from, at least even if we haven't had this background right here, right? Because it's not going to be a crucial thing for you to understand this part. But that's our formula, and that's where it came from. We integrated the spring force in order to get a final result here. This is work done by spring. Okay, and we'll be using that down the pipe when we talk about potential and kinetic energy. Which brings me to my next bit here. Anybody need to see any of this? So from this slide, just write down this formula. This is the work done by a spring. This is force times displacement, which is work in definition is force of any force over a displacement in the same direction. So the spring force, even though it goes opposite, still in the same axis. So the spring can do work. And this is the result. Okay, so next thing, some of us, came after school Monday. We saw a little bit of this, so let's go back over it. This takes me to my next topic, section 7.5, basically, which is kinetic energy and the work-kinetic energy theorem. So I guess I can squeeze the title up here. Kinetic energy and the work kinetic energy output theorem for short. That's section 7.5. So we were talking about the concept of work done by a force. So say that we had a box and it's being pulled to the right or for a displacement. And we know that that force is going to provide work because in this case, the work will be positive because the force and the displacement are parallel to each other. The angle between them is 0, and we know the generalized equation for work is F cosine theta delta x. And since the angle is equal to 0 in this situation, then cosine of 0 is going to be equal to 1, and we just reduce down to this work equation F net delta x. Cosine of 0 is just 1, so it's redundant. You multiply by 1, you understand it to be 1. So we got this force moving to the right. It's pulling this box to the right. The work done by that force, F net delta x. We also know from Newton's second law that F net is equal to mass times acceleration times delta x. So this net force is equal to mass times acceleration. It's obviously because it's changing its velocity from, let's say it was at rest, and then that force is going to be moving it from rest to some non-zero velocity. Therefore, it's going to accelerate it. So therefore, the net force is mass times acceleration, delta x. Is there a way, I mean, we get to this form. And you might say to yourself, I mean, if you're seasoned enough with your math or even physicists, to whatever degree you are, you might think to yourself, hey, is there a way I can simplify this even further? And because the job a lot of times is to make things as simple as possible. And yes, you can. You can definitely make this simpler. So we have ma delta x, motion diagram, constant acceleration to the right, the velocity is increasing. We can simplify this expression a delta x in terms of a kinematics equation. Why would we go to kinematics in this sense? Well, right, we are changing its velocity from something initial. Let's say that the initial velocity was 0, the box was at rest, and I start pulling it to some final velocity under a constant net force. Therefore, I'm accelerating it. So I can embed kinematics into this work equation to simplify this ma delta x equation that I have here. And the one kinematics equation that involves going from initial speed to final speed with our context here is the VF squared equation. So VF squared equals VI squared plus 2A delta x. Let me solve for A delta x here, and then I can substitute back into my original equation, and I get a new work equation because I'm curious and I want to simplify it. So I subtract both sides by VI squared, VF squared minus VI squared divided by 2, because this was once 2, and left 2A delta x over here. So I divide both sides by 2, right? So I get rid of that. So A delta x is equal to VF squared minus VI squared divided by 2. That's my expression for A delta x. Now I'll go back to substituting at the top there. So net work is equal to MA delta x. MA delta x is equal to this. Simplify everything out. I get my famous equation for kinetic energy, 1/2 m v final squared minus vi squared, which in this case is a change of kinetic energy. From the definition, kinetic energy itself is equal to 1/2 mv squared. If my object was moving at a constant velocity, and of course it has mass, I can calculate its kinetic energy. But if the velocities change, there's a difference in the velocity, I can get the change in the kinetic energy. So it stands to reason then that net work, which is equal to F net delta x, is also equal to a change of kinetic energy. This is what is known as the work-kinetic energy theorem. Okay, the marriage between work and kinetic energy. And we're going to see further the marriage between work and potential energy, which we'll talk about next week. And then we will marry both potential and kinetic energy together to get the grand conservation of energy. So, step by step. Questions on the parts here? We follow from the top the derivation of work into F net delta x into change in kinetic energy. you should ask now if you have any questions, because I don't want to see 3 weeks later. I didn't know what was going on here. That's why we gotta stay in. But if there's no questions on that, that's great. Excellent. So this is what 7.5 is all about. Work kinetic energy theorem. Work is equal to the change of kinetic energy, which is also equal to F net delta X. And I think we went through some examples. Right. So let's do an example, the same example. I think it may have just been Lily. You probably weren't here, the only one here last time when we went over this stuff. And so we went to page 191, number 29, and talked about that. So we have this 0.6 kilogram particle has a speed of 2 meters per second at point A, whatever point A is, and kinetic energy of 7.5 joules at point B. Okay, so mass 0.6, write down stuff that we know. At some arbitrary point A, this we can take a picture of it, measure the speed at that point. It's 2 meters per second at that point. Kinetic energy at B is, take another picture, 7.5 joules. Here's A to B, change in kinetic energy here to there. Then it asks us, what is the kinetic energy at A? Well, we have the velocity at A. We know what the mass is. Put in your equation. 1/2 mass times V squared. You get 1.2 joules. And then, yep. And I said, okay, let's do B and C. And I think Nicole and others came up with the answers and said, okay, let's prove that B is 5 meters per second and C is 6.3 joules. So we went to B and we're trying to figure out what the velocity is at point B. So we have the kinetic energy, 7.5 joules, know what the mass is, solve for the velocity, 5 meters per second. How do we do that? Just took the kinetic energy formula and multiply both sides by 2, divide by mass, square root, and 5. And then letter C, again, that work is equal to F net delta X, which is change in kinetic energy. Change in kinetic energy is final energy minus initial energy. And then you subtract. So it all marries together. When you have a force and displacement, you can find the work. When you don't have that and you have just the velocities and the mass, you can find work also. It's the same thing, because when you apply a force over a displacement, you are changing its kinetic energy. Hope you see that. And even if the velocity was non-zero in the beginning, you changed it from 2 meters per second to 5 meters per second, as we see stipulated in this exact example here. We've changed it from 2 to 5. We've accelerated it. We can find the acceleration in the system. We can find how much time it took to accelerate it. We got the energy. We can find force. Find everything. And since the change, and since the force wasn't constant, it's not going to be a constant velocity. You can find acceleration. Yeah. So all that. Questions? We did 30, same thing, same logic. So that's what, we introduced the WKE. I want to talk about the spring force, the spring energy. And the next week, we'll get into potential energy, where we will totally be using the concept of system to relate potential energy, gravitational potential energy, to kinetic energy. We're going to see how they relate, work together in this concept of work, and go from there. Right. So another thing I want to say about the work done by the spring force. Let's see. Yeah, this guy here, the work done by the spring. We'll see this also referred to as elastic potential energy. We'll get into concept of potential energy later. Elastic because the spring is, well, an elastic, you know, thing. It changes shape, stretches and compresses over a displacement x. Okay, so let's now get to the beginnings of our skills test for the day. I said it's projectile motion, and let's use the rest of the period for that. And I said I was going to set it up and give you the first couple of steps. At this time, a separate sheet of paper and set up the skills test.